So good
Yeah,
morning to okay. So good morning to everyone. So this is the third day for the AICT IST sponsored induction orientation program on machine learning, which is conducted by the Department of Information Technology UIT CSJM University. And I would like to introduce and welcome Dr. Anukriti Bansal ma'am. Ma'am is an assistant professor in the Department of Computer Science and Engineering at LNMIIT Jaipur. Her broad research areas includes image processing, machine learning, pattern recognition. She has earned her master's from University of Rajasthan and PhD from IIT Delhi. She has published various papers in international conferences in renowned journals of repute. It's a pleasure to have you here, ma'am, as one of the speakers to this particular workshop. I welcome you and request you to benefit the audience with your knowledge and experience. Thank you very much. And now you could begin, ma'am. Thank you.
so first of all, thank you so much, Dr. Rashi and the complete team, organizer team, who has organized this workshop and invited me for this talk. And in today's session, I will talk about artificial neural network. Will it be fine if I close my video because there is a bandwidth issue? It's Sunday and I'm
Please,
at home.
please do, please.
Sure.
Thank you. Yeah, so first of all, thanks to all the participants as well. So because they have spare time on Sunday, especially for the session. So I hope, let me start. I hope my screen is visible.
Yes, ma'am.
Yeah, okay. So first, before I begin, I want to acknowledge that these most of this content of this presentation, the slides have been inspired from Professor Mitesh Kabra's course CS7015. Now, this is the brief outline of the course. We will first talk about the brief history of neural networks, how it was developed, and then we will talk about the first computational model, which we can call as the first neural network model, which was inspired from biological neurons. After that, we will talk about the perceptron model, which help us in understanding of multilayer perceptron, which can be considered as the core of today's deep learning architectures. We will also talk about how this learning algorithm, how these deep neural networks learn, and then we will have a small hands-on in Python. So before talking about artificial neural network, the question comes, why we want to study about deep learning? What is so fancy about it that today everyone is speaking about it? So let's understand this with a small comparison with the traditional learning pipelines and the machine learning pipelines. So in traditional learning, suppose if I want to identify different fruits or recognize different fruits. So what I have to design handcrafted features. What handcrafted features? That the color should be, suppose if I want to differentiate between orange, apple, and banana. So I have to specify that the shape should be elongated for banana, the texture should be smooth, color maybe is yellow. And then I have to design these handcrafted algorithm. That is, the color is uh, maybe yellow and the texture is smooth and the shape is elongated, then consider it as banana. Otherwise, for different fruits, I have to design these handcrafted features and also algorithms. Now, the problem with this approach is every time I want to design an algorithm to classify for a new fruit, suppose I have to change all these features and all these algorithms, and it is not scalable and robust. Okay. So then came the machine learning pipeline, which till 2000 was very popular. or maybe 2010, the machine learning algorithms were very popular. Why? Because we have this learning become automatic. Now what we need to do, we have suppose apple and bananas, but we have to specify, okay, these are the features. Now learn the rules automatically. So the system, the machine algorithm was able to learn the rules so that it can differentiate different fruits on the basis of these specific features. Now, this was fine, this was okay, but consider your Aadhaar cards. In Aadhaar cards, you all know that when we go for the application of Aadhaar card, they take our retina scans, fingerprint scans, and with these features, they are able to distinguish each and every person. Considering only the population of India, if we go for these machine learning algorithms, doing these handcraft features may not be very trustworthy approach, because it may be possible for us that maybe there are 100 features which are right now working fine to distinguish or able to classify among maybe 1 lakh or 2 lakh people, but when we talk about scale, maybe they are not sufficient. So we want some algorithm similar to our mind, which is able to learn these patterns, these features on their own. So there comes this, sorry. So there comes, so there comes this deep learning pipeline. So this deep learning pipeline help us to learn the features on their own, and then we can like learn the algorithm as well, like how this feature is how this learn feature. For example, instead of giving features, now what will I do? I will only give the picture of different apples, bananas and oranges. Now what are the specific features which help me to distinguish between these fruits? Algorithm will learn these features on its own, and also it will categorize these features on its own. Okay, so when we talk about scale, when we talk about your YouTube, where we can search for where we can see that whenever we look for similar kind of features, it provide us recommendations. So all these things are possible with deep learning approaches only. So okay, this is deep learning, which we will be studying, artificial neural networks, which we will be studying in this lecture. But what are artificial neural network? What we will be studying today? So we will be studying whole this network. Okay, it may look scary to some people who have not exposed them to deep learning frameworks. But what if I say that instead of learning this complete network, how this learns, what is the input, what is the output, how this learning is going on, instead I say that I will only talk about this single neuron. I will only talk about this single unit. Then it makes sense. We can think of staying in this lecture or in this session for some time, because then, okay, it is easier to do. Okay. Because why? If I am able to understand, if I am able to have the idea of this single, if I am able to have idea of this single unit, all these things are repetitive, you know. So then the working of neural networks would be easier. Understanding the working of neural network would be very easy. So let's first talk about a brief history of neural networks, and it will help us in understanding like how this the current architecture which we are viewing is there. So, surprisingly, when we talk about neural network, we think that it is like has been developed in recent decade or past 2 decades. But surprisingly, ANNs are or artificial neural networks, they are around for quite a while. They were first introduced in 1943.
Your screen is not visible, I think.
Okay, okay, let me just check. Okay, okay. So, yeah, so after McClock and Pitts, then it was very popular, and this became even more popular with the introduction of perceptrons in 1950. After that, in around 1960s, some issue was identified in these perceptron model, and due to which it suffers a long dark age, or suffers a long winter, we can say. In 1980s, there were revival of interest in connectionism, but at that point of time, machine learning techniques were more popular, such as support vector machines. And they were even more, why they were popular? Because they have very strong mathematical foundation to back on. And again, this artificial neural networks, if you can see, it suffered a long winter period until 2000. After that, this gained popularity, and after 2006 and 2010, whatever challenges we talk about, maybe it is object detection, object recognition, prediction, everything, every challenge is won by one or other deep learning based algorithm. Now, one question arises here. After checking all this historical advancement, can we think of that this artificial neural network will again like see dark age? I think now it's a different time. There are multiple reasons why it is a different time, because right now we have huge amount of data, and to process this data, the computation power we have these days, like GPUs, TPUs, everything. So it is can be considered that this right now this ANN will stay with us forever, and most of the tasks these days will be done using artificial neural networks. I'll not go into the applications of artificial neural network. I think that part has already been covered. So let me come to the basic understanding. So as we have seen here, instead of understanding all these complete architecture, it may scare us, but if we try to understand the small units, the single units, all these units are doing the similar kind of task in the whole network. So if we identify, if we understand how this uh, each unit is working, what is there inside this unit, I think then understanding this whole network would be easier. So this was the first architecture, first computational model proposed in 1943 by McClock and Pitts, and which can work similarly as we talk when we talk about biological neuron. Now, what are the chief characteristics of McClock and Pitts neuron is that it can take one or more binary inputs and then produce one binary output. So these binary inputs can be excitatory or it can be inhibitory. Now here, what do we mean by inhibitory? Let's understand this. So inhibitory says that irrespective of what else is on your input feature, what else is on in your input features, if this inhibitory is on, your output will always be 0. So for example, these are my features. These are multiple binary units which I am providing to my neuron. And this neuron has multiple n number of inputs. These take the summation of these n number of inputs, and on the basis of certain threshold value, suppose I want to decide for whether I should go for a movie or not. So there can be multiple number of binary inputs. I can have that whether this movie is of thriller genre. Second, whether this movie is directed by maybe Sanjay Leela Bhansali, or maybe it's a 3D movie or 2D movie. So there may be certain parameters on the basis of which I will decide. So there are certain level of inputs. Okay. Now, on the basis of these 3 or 4 inputs, I can decide a value. Maybe if, okay, 2 or 3 condition are matched, then I'll go, otherwise I'll not go. Okay. So this is represented by this X values. These are my binary inputs. Now here, when we talk about any inhibitory, so if I say whether I am ill or not, so if I am ill, irrespective of all other conditions are matched, I will not go for the movie. Okay, so this is the meaning of excitatory and inhibitory input units. And this theta is a threshold value. So in our movie example, if we consider that out of 4 conditions, suppose 2 conditions are matched, I'll go for a movie. Otherwise, I'll not go for the movie. Okay, so this was the simple Matlock and Pitts a neuron which was able to implement, which is able to take decisions on the basis of number of binary inputs. Now, let's talk about some of the Boolean functions, using Matlock and Pitts neuron. Now, the question you may ask is why we are interested in Boolean functions using Matlock and Pitts unit. We are interested in Boolean functions because we have oversimplified the way we want to take decisions. So we have number of parameters, but the output of these parameters will be yes or no. So genre is thriller or comedy, yes or no. Whether the movie is on Inox or maybe other Cineplex. Whether it is directed by Sanjay Leela Bhansali or maybe some Karan Johar. So on the basis of these decisions, I will decide whether I want to go for a movie or not. Okay, so that's why we have oversimplified the way we are taking the decision. Now, so if we talk about the first function, AND function. So this AND function, it takes 3 inputs. It takes the sum of these 3 inputs, and on the basis of this sum, it will decide whether output should be 0 or 1. So what should be the threshold value? Theta. In case of AND function, anyone wants to answer? In case of AND function, if you want to suppose simulate the AND function, what should be the theta value? It is written here, it is 3. Why 3? Because we know if we have AND function, all input values should be 1. And if all input values should be 1, then only it gives output as 1. So here the threshold is set to 3. So if the sum of inputs is greater than or equal to 3, it will fire the neuron, means it will give output 1. Otherwise, it will give output 0. Okay. Similarly, we can have OR function. As we know, in OR function, if any of the input is 0, any of the input is 1, the output will be 1. So here we have set the threshold as 1. Okay. And there are another implementations. This dot, this circle here I don't know whether it is working or not. The circle, the bubble at the top of this line in the fourth function, it says that it is the inhibitory input. And as discussed earlier, it will give the output as 0. Okay. So it will give output 0 and it will implement all these functions. Now, so the question arises, can we implement any Boolean function using McClock and Pitt's neuron? So before answering this question, we will see a bit of geometric interpretation of what McClock and Pitt neuron is actually trying to do. Okay. So let us take this OR function where you have two inputs, x1 and x2, and this neuron is going to fire. Okay. Now, it says that x1 plus x2 is greater than or equal to 1. It will going to fire when this condition is met. Now, for time being, just forget about this greater than sign and just consider the equation x1 plus x2 equal to 1. So, what this equation means tells you, what is the equation of, what is this equation of A? This equation x1 plus x2 equal to 1, if we just see this equation, this is an equation of a line. Okay. So now in this case, since we are dealing with Boolean inputs, we have two x's, x1 plus x2. Okay. So, and for these two x's, we have only 4 inputs are valid, because we know that we have, these are not real x's, these are Boolean x's, these are Boolean functions. So for these two x's, x1 and x2, we have 4 points, 0, 1, 1, 0, 0, 0, and 1, 1. Okay. Now, now we want to know that we want a decision boundary. Okay. So what we want that all those points for which the output is actually 1, they should lie on one side of the line, and for those whose output is 1 should lie on the another side of line. So can you see how many points here lies on or above the line? Anyone wants to answer? If we see here, I don't know, my cursor mouse is not working right now, but here we have 0, 1, 1, 1, 1, 0, and 1, 1. So these 3 points lie on the line or on the right hand side of the line, and this point 0, 0 lie on the left hand side of the line. So we get a decision boundary accordingly. We are able to segment these 4 points using a line. So we have a proper boundary here. So if we talk about the simple classification problem, binary classification problem, whether it is an apple or banana, there should be a line which able to divide the instances of apple on one side of the line and instances of banana on another side of line. Okay. So same thing we are able to implement here as well. We have a proper line, linear separability is there among these 4 points. Okay. So we can take another example. We can take the example of AND function. If we take the example of AND function, you can see that here the threshold is 2. Why? Because we have 2 inputs and the neuron will fire only if these inputs, both the inputs are 1. So here we have the equation of line as x1 plus x2 equal to 2. Okay, and this decision boundary will pass from 0 to 2, 0. Okay, so this is the decision boundary, and we can see that the points which gives output 0 lie on the left hand side of the line, and the points or the inputs, the combination of inputs which gives output 1 is lying on this line itself. Okay, so we can say that, yeah, most of these Boolean functions can be uh, can we can have a linear separability between these points on the basis of Matlock and Pitt's neuron. But what if we have three inputs? If we have three inputs, we can have like a plane. If we have more than three inputs, we can have hyperplanes. Okay, which help us in division of points on one side of the plane and another side of plane. So far we have discussed that a single Matlock and Pitt's neuron can be used to represent Boolean functions which are linearly separable. Okay, that we have already seen. Now, right now we have said that the input values which Matlock and Pitt neurons take, it only takes binary values, either 0 or 1. And also this threshold theta, we have to hand code it. Okay, if we talk about real world situations, suppose we talk about our example of watching, whether to decide whether we want to go for a movie or not, then it may be for that particular example, yes or no may be fine. But suppose I want to I want to design a model for prediction of rainfall. So here we have different parameters which may not be binary, which have real values. Maybe what is the humidity, what is the pressure, what is the wind velocity, what is the temperature. And these values, these input values are not binary. We cannot represent these input values as binary values. Okay. So in real world, to solve real world problems, we need real input values. And also, it is very difficult to hand code this threshold value in Boolean values. Okay, we can decide this threshold value, but what if we can learn this threshold value automatically? And also, these input values should have different importance. For example, uh, if I talk about whether there will be rain, so there, when we talk about Indian Meteorological Department, they take care of many kind of features or input parameters. So they take care of wind velocity, pressure, temperature, and humidity, and n number of other parameters as well. But there are certain parameters which affect more as compared to others. Okay, so for me, if I want to go for a movie, so, and if I see that, okay, the actor in this movie is suppose X, so whatever are the other parameters, my preference for that particular actor will be more as compared to other parameters. If the director is some another person, or maybe the genre is different, but if the movie is acted by one particular actor, I will definitely go to watch that movie. So there is a different weight to different inputs. How can we do this in neuron? How we can implement this thing in the neurons? So then, to answer such questions, Perceptron model was developed in 1957, and later it was refined by Minsky and Papert in 1969. So the 1957 perceptron model, it is called as generally a classical perceptron model. And when we talk about the perceptron model, and throughout this lecture as well, we talk about this refined version of the perceptron. Okay. So now, can you see the difference between these this model and the previous one which we have discussed? You can unmute, please free to unmute yourself and answer if you want to. It looks very similar to the previous one, but what is the difference here?
More number of outputs might be.
So output is just a 0 and 1. It was previously as well, we were like doing either 0 and 1 as the output. So tell me,
N number of input.
n number of inputs were also there. So this was my diagram of Matlock and Pitt's neuron. And this is the diagram for perceptron. So can you see something like W1, W2? It was not there earlier. Yes or no?
Yes. That is, we are calling that is width.
Yeah. So
Yes.
the perceptron model, this says that the inputs which we want to give more importance to some inputs as compared to others. How we give this differentiate inputs on the basis of these importance? On the basis of weights. We assign weight to each and every input. Okay. And also these numbers, these input values, they can now be a real values. Instead of binary inputs, now we can have real values as well. Also, they also introduced how we can learn these weights automatically. Okay. So this was the perceptron model. And other things, instead of summation of inputs, now we have weighted sum. And if you can see, I equals to 1 to n. Okay. So we have n number of inputs and we take their weighted sum. If their weighted sum is greater than a particular threshold, theta, then it will fire 1. It will give output 1. Otherwise, it will give output 0. Now, after the refinement, the more accepted convention is this. So if you can see here in the red line, we have introduced one more thing, which is called x0 equal to 1 and w0 equals to minus theta. How this has come. So let me see if I am able to write. Just a minute. So here it is not possible, I think. So anyway, so what I can do is, Emma, is my screen is still visible?
No.
Okay. Now is it visible?
Not yet.
Okay, now it should be visible. So the more accepted convention is, earlier we have this equation, okay, and we say that if this value is greater than theta, it will give 1, otherwise it will give 0. Okay, if we bring theta here, so it will be summation wi xi minus theta is greater than equal to 0, or then output will be 1, and summation wi xi minus theta less than 0, then its output will be 0. If we want to write this more formally, I can write it like this. So here, if you will see, now the inputs have from 0, and we have introduced one more term here, which is W0. W0, this term is called as biased. Okay, and this theta, this x0, this input value will always be 1, and this W0 equals to minus theta. Okay, or minus theta or the threshold value. Now, why we want to do this? Why is W naught equals to minus theta called the bias? So the bias represent the prior information. So when we design some learning based algorithm, we have data set. Okay. So maybe if I want to decide whether I want to design a system which tells whether I want to go for a movie or not. So let's talk about the binary inputs, though it can take real inputs as well. So let's talk about there are n number of features, but there is some prejudice that, okay, if this is the actor, I will definitely go to watch a movie. How to put this prior information? So that can be done using this bias term. This W naught is more popularly called as bias. It helps us in adding this prior information. Okay. So let's talk about first the difference. We had Matlock and Pitt's neuron, and in which it takes input values, take its summation, and if the values are greater than a particular threshold, it gives 0, and otherwise it gives 1. Perceptron also we are doing the same thing. The major differences are that we can have real values, and also we can have weights, and these weights can be learned. Okay. So these are major difference, but one thing we have to verify is that whether this perceptron can be used to implement a function which is linearly separable. Okay. Separable means it is able to divide the points like this. So if we take these points and suppose we have chosen these particular set of weights and a threshold value, then we can have a line which help us in implementing this OR gate. 3 points which lie on the right side of this line or on above this line, they will output 1, and the point which lie on the left hand side will output 0. And we can have more n number of such lines. We can have 1.1, 1.1 x2. We can have 1.2, 1.3, 1.5. All these lines. There can be n number of these weights which help us in giving this equation. Okay. So weights, various solutions are possible. So yes, this perceptron model is giving us a function which is linearly separable. Now again the question is how to identify what weights we need to have. So when we randomly choose some weights, okay, so suppose we have taken weights W1 equals to -1 and W2 is also equal to -2. So if we draw a line, so this is the line. Okay. So if this is the line, how many errors we have? What is the error in this case? How many points will be wrongly classified?
Actually, all might be that all the points are we are not segregating means for 0 or 1. I think so.
So we make,
Means all the input.
see, if we have this line, so our notion was this. See, so 3 points. So the points which are on the right side of this line or which points which lie on this line will give output 1, and the all other points which are on the left side of this line will give output 0. If see this equation, so there are 3 points which are on the right hand side of this particular line. So they are correctly classified, I can say, yes or no? if we see only this particular line, are you able to see this cursor value?
Yes, ma'am.
So there are 4 points which lie on the right hand side of this line, and there is not a single point which are on the left hand side of this line. And how many points should actually lie on the right hand side on this line? असल में कितने पॉइंट्स होने चाहिए थे राइट साइड में?
Only 2.
3 होने चाहिए थे ना? If we talk about all this, if we talk about this line, तो हमारे
yeah, okay.
3 होने चाहिए थे.
Single point. एक ही point होना चाहिए था बाहर. 0 0.
एक पॉइंट लेफ्ट साइड में होना चाहिए था. ठीक है? तो अभी हमारे कितने हो रहे हैं? चारों पॉइंट राइट हैंड साइड में हैं. तो हमारी एरर कितनी हुई?
3. Oh,
एरर
sorry.
हुआ ना?
हाँ, एक ही हुआ.
तो अगर हम अब ये वाला देखिए, नेक्स्ट एग्जांपल 1.5 and 0. So this is this line. So if we talk about this line, how many points are on the left side and how many points on the right side? So what is the error in this particular case?
There is an error again 1. That is 0 1 को भी 1 होना चाहिए, तो वो है, और 2 points each side है.
Very good. Yes. So now the error is 1. Again, let's talk about this third line. So what is the error in this case?
All 4 are the errors because
all 4
चारों points बाहर गए.
नहीं, but ये वाला तो सही है ना? It is on the one side of the line. 3 are on the wrong direction. So error in this case is 3. Okay. So this is how we decide, like we initialize W1 and W2 with some random weights. We see whether we are able to get the outputs. So error should be 0 ideally. Okay. So if we get error 0, that means the output is correct. Otherwise, the output is wrong. Okay. So now how to learn these weights? Right now we have just seen that we are randomly picking some weights and see whether the output is correct or not and what is the error. But this perceptron model, the beauty of this model was that it was explained how these weights can be learned automatically. So let's see this information. We have weights, n weights. We are including, right now we are not, we are including this bias term as part of your input only. Okay. So we have n weights, n plus 1 weights and n plus 1 input value. And we have some data set as well. So if you talk about that movie example, if I want to decide whether I'll go for a movie or not, if I want to learn the importance of whether genre is important for me, whether the actor is important for me, whether the director, what is the importance of the director in deciding whether I'll go for a movie or not. So, so I have this examples, previous preferences, and I also had labels. अगर ये options थे मेरे पास में, तो मैं movie देखने गई थी या नहीं गई थी. Okay, whether I'm interested in watching a movie or not interested. So these are my labels. So positive labels, that means I'll go to watch a movie. Negative label, that means I'll not go for a movie. Now initially we randomly initialize some values to these weights. Okay, and then we will try to update weights till we reach convergence. Now what do we mean by convergence? Convergence means that when we have classified all new examples correctly, okay, whether now for different sets of these movies, actors and features, whether my algorithm is able to correctly classify whether I'll go to watch a movie or not. Okay, so first we randomly choose a training case. This W belongs to P union N. So that means from the complete set, I choose a training case. it says that if the perceptron predicts 1, X belongs to P, that means label 1. So if the perceptron predicts a 1, and it should have predicted 0, okay, because this is less than 0. So it should have predicted 0. So then what I'll do, I will add the input vector to the weight vector. And similarly, I'll do the reverse. In other case, suppose my perceptron has predicted 0 and it should have predicted a 1. So let's see whether this equation works or not. Since the time is less, I provide you with an example. I'm not able to write. I thought that I'll be able to write here. So you take some initial example. Suppose X you take at 0.3 and 0.4, bias as 0.5, weights 2 and -3, and you try to solve it. And in next iteration, whatever weight you are getting right now, whatever value you are able to predict right now, if you update these weights, whether these weights are decreasing or not. And once these weights become 0, that means we are our predicted output matches with the original label. That means we have reached the convergence. Okay. So right now, till now, we have seen that whatever the limitations of your McClock and Pitts neuron, that only binary inputs were allowed, and the threshold value was we were not able to learn it on our own. That has to be hand coded. These things can be dealt very cleanly, beautifully with perceptron model, and it also provides us a linear separability. Now, the Minsky and Peppert in 1969, it highlighted one of the major limitations of this perceptron model. It says that this is incapable of solving XOR classification problem. This XOR classification problems comes under the nonlinear problems, though logistic regression and another similar kind of machine learning algorithms also are not able to perform well for nonlinear kind of problems or XOR kind of problems. But the thing is that people have very high expectations from this perceptron model. So once this limitation came, this whole idea of artificial neural network went into a long winter until, you can say, 2000s. Okay. So what this XOR problem is, if we take two inputs, if we initialize, if we take some weights, okay, and if we see this input, we can say that this condition 4, which says W1 plus W2 should less than equal to minus W0. This minus W0 is nothing but your threshold value, theta. Okay, it is less than, and it contradicts with this second and third condition. And if we see this diagram also, we cannot draw a line, we cannot draw a single line which is able to classify these points properly, like zeros on one side or ones on another side, because we don't have a linear separability in this particular case. Okay. So then what's the problem? How it can be solved? So this limitation of perceptron was eliminated, that if we stack multiple perceptrons together, this problem of XOR can be overcome. And this gives the origin of multi-layer perceptron model which is the core of the deep learning models which we see today. So here, this is a layer of perceptron model. This is a single layer of perceptron model, and which is stacked by another perceptron. Okay, so in general, we can say that perceptron if we talk about very simple perceptron, it consists of a single unit or single neuron. And generally, perceptron is a single layer of perceptron model. And when we talk about multi-layer perceptron, we have multiple layer of perceptrons. So in this particular case, we have two layers. This is one layer of perceptron and this is another layer of perceptron. Okay, this is our input. In today's conventions, we say that this is my input layer, this is my output, and this is hidden layer. Okay, and what is there inside each neuron? Can anyone answer now? What is there inside this each neuron?
Hidden layer.
No, what is there inside this whole set of neuron is called as a hidden layer, but what is there inside this neuron? What is there inside this perceptron?
Weight and
So it has this DNA.
inputs.
It has this DNA. The first part of this perceptron, first part of this hidden neuron, first part of neuron, what it will do, it will take the weighted average. And the second part, what it will do, it will threshold, it will do the threshold. And since it is doing a threshold in terms of 0 and 1, we can say that this is a binary threshold unit. Okay, this is a step function which either gives me 0 or it will give me 1. Okay, so now you should not like be scared when you see large number of units. This is nothing but the simple thing. It is taking a weighted average and then it is doing thresholding, taking a decision, giving the output on the basis of certain threshold. Okay, is this clear? Each of this is a perceptron, single perceptron. It will take the weighted average of all these x's and then it will give 0 and 1 on the basis of the threshold value. Similarly, this also takes input from these units and take their sum, do the weighted average, and then give the output on the basis of step function, or I can say the threshold value. Now, it is more convenient that we pass input to these pass-through neurons. These pass-through neurons are called as input neurons. They do nothing, but whatever input they receive, suppose they receive this x0 is 20, x1 is 40, x2 is 60. So what they will do, this input neurons, they will only take these values and give these values as it is. So the output of these pass-through neurons will be same as the input. So 20, 20, 30, 30, 40, 40, so on. Okay. This layer is called as input layer. This layer is called as your output layer. And this is called as hidden layer. Is this terminology clear to everyone? Okay. So now this network which contains this input layer, output layer, and one or more hidden layers, it is called as multi-layer perceptron. So this is also a multi-layer perceptron with one hidden layer. This is multi-layer perceptron with two hidden layers. Or in fact, we can call it as 3 layers of perceptrons. Here we have 2 layers of perceptrons. Here we have 3 layers of perceptrons. Now, some basic terminologies that people use these days. when all the neurons, if we say these are biased neurons, okay, I'm not talking about these. I'll talk about this later on. This X0 is a biased neuron. Its value is always 1. Okay. So all these, when all the neurons in a layer are connected to every neuron in the previous layer, it is called as fully connected layer or a dense layer. So how many dense layer we have? We have 3 dense layer. First one is this, because each neuron in this layer is connected to each neuron in the previous layer. So this is one dense layer, this is another dense layer, and this is the third dense layer. Here you can see that the output layer has 3 neurons. So what it can do, this particular multilayer perceptron can classify simultaneously into 3 different binary classes, okay, which makes it multi-output classifier. What do we mean by multi-output classifier? Suppose we have some medical data that a person has person smokes, he takes tobacco, and he drinks. Sitting habits are so and so. So these are my features. Now I can predict whether the person will have diabetes or not, whether the person will have some heart issues, yes or no. So it can generate these multiple outputs. Yes, the person will have diabetes or develop diabetes in near future. The person may develop heart problem in near future, yes or no, and some another output as well. All these are binary. Okay. So this is, now we can see, we want to check whether this multilayer perceptron can solve XOR problem, because most of the real world problems, they are non-linear. And if we want to solve non-linear problems, this multilayer perceptron should be able to work in these scenarios. So this, you can work on this situation. Since time is left, I'm not going through it, but here are input values. You multiply these, you take the weighted, these are weights of each connection. You check whether you are getting output as desired. Okay, this is exercise left for you. So now we can say that multilayer perceptron with a single hidden layer can represent any Boolean function. Okay. Now, right now we have like solved some of the limitations. Like if we talk about McClock and Pitts neuron, it was able to take only binary inputs, and the threshold has to be hand coded, and it was able to give binary output. Then there comes the perceptron model. It was able to take real values. The threshold, it provided us an algorithm which can learn those threshold or weights automatically. It was able to generate a binary output. Okay. And the problem was, it was not able to work in case of non-linear problems. Then we have multilayer perceptron. Rest apart all the things, it was also able to solve non-linear problems as well. But again, one more thing is, right now inputs are real numbers. My output is again binary, 0 and 1. So can we have some model where we can have output as real numbers? So there comes the role of activation functions. So if we, so before coming to the activation function, just recall that a perceptron will fire only if its weighted sum is greater than a particular threshold. Okay. And
okay, I found this on the web for if it's weak.
And this thresholding logic can be very harsh at some times. Why? Suppose I talk about a single neuron, okay, single perceptron model maybe. Its biased is 0 and it's weighted, it is only taking one input. Okay, and weight is 1. So there is some error. I'll correct it. Now, if suppose I have input values 0.49, my rating for a movie, maybe it's 0.49 and 0.51. So these two values are very close to each other, but Perceptron will assign different labels to them. It will assign 0 to 0.49 and 1 to 0.51. When we talk about real world problems, the transition is not so abrupt. We never talk about only 0 and 1 kind of things. There is certain kind of similarity in these two values, which my perceptron model is not able to capture. So here comes the activation functions. So here we would expect that decision, this threshold value should not be a binary value, and the decision should be a gradual change from 0 to 1. This particular example, which was the first activation function, is of a sigmoid activation function. Okay, so from threshold values, it gives us the smooth function. From strict threshold values 0 and 1, it gives a smooth transition. In case of sigmoid, these gives us a probability. These gives us a value from 0 to 1. With the time, other threshold functions were, other activation functions were also designed. So we have sigmoid function, 10H function, and rectified linear units. So now the output range is a real value between a certain range. So when we talk about a sigmoid function, so it is between a certain range, 0 and 1. When we talk about a 10H activation function, the output will be in the range of -1 to +1. And same when we talk about ReLU activation function, the output will be 0 to 1. Apart from giving this non-linearity, apart from giving a real output value, one of the very important property of these activation function is that they are smooth, continuous, and differentiable. Why this differentiability is so important? Because we have seen that in Perceptron, we had a learning algorithm which help us in learning those weights properly. But we have not talked about how these weights will be learned in case of multi-layer perceptrons, because we have these hidden layers as well in between now. So how to learn these weights? And this was the problem which was like, which stopped this popularity of artificial neural network for some time. Researchers struggled a lot, and then in 1986, Hinton, Williams, and Rumelhart, they proposed backpropagation algorithm, which allow us to learn these parameters. And what are these parameters? The biased value and these weights, most importantly, to learn automatically. And this multi-layer, this algorithm is based on this gradient descent. So I'll briefly talk about what do we mean by gradient descent, because if we understand the gradient descent approach, we will be able to learn the backpropagation algorithm to learn the weights of multi-layer perceptron as well. So what happens is, if we take this slope will be given by these gradients. Okay, derivative will give us so we start with some initial value. Okay, and we take its gradient and move a little, update the weight. So right now, don't think of this value eta. This is the next line. Sorry. So WT plus 1. So the weight on the next time will be given by the current weight minus gradient of the current weight. This eta we will talk about a little later, but this is how we are updating weights. So we start with this and we move in the negative, towards the negative of this gradient. Whatever value we get, we update the weights accordingly, and we keep on doing this till there are no changes in the weights. Weights are not getting updated, or we have reached some maximum iterations. So ideally, after certain amount of iterations, we say that we reach a point where this value, this error is minimum, and the weights are optimum. Weights are optimum means we have already seen the during perceptron minimum weights. That means weights are not changing, means the error, we have reached a point where the error is less. Okay. And in real world situation, we don't talk about zero errors, but the minimum error. Okay. So these theta are the parameters which we want to update, and this is the cost. And at some point of time, we will reach this minimum cost. This is the gradient descent. Now here, this eta is the learning rate. This learning rate is nothing but the steps, the amount by which we want to change these weights. Now you can visualize if we take this learning step very large. So, okay, we have to do very less number of computations and we may reach minimum very quickly. But it may possible that when I reach here, the next learning rate will give me here, and I'll keep on bouncing like this. Okay, if I take large step, I may not able to reach the minimum value, but maybe I may bounce it here, again here. So I'll keep on bouncing. In contrast, suppose if I take a very small step, in that case, it will take very huge amount of time, very huge amount of computations, and it may possible that this is very ideal curve, but in real life situation, we may have some areas which looks like minimum value, but it is not actually a minimum value. So if the learning rate is very small, we will stuck to that local minima. We call it local minima. Instead of reaching global minima, we stuck in the local minima in case of learning, if the learning rate is very small. So this is it is one of the very important hyperparameter. It is a design paradigm. So generally what we take is, we take dynamic learning rates which take more or big steps in initial iterations, and later it keeps on decreasing those steps, like the changes we are making are small. So it is computationally also efficient, and even if we stick to a local minima, it helps us in coming out of it. Now, once we have some idea of gradient descent, we can now talk about the algorithm which help us in learning these weights. So these are the weights associated with layer. So I can say this is input layer, but if we talk about the layers of multilayer perceptron, layers of perceptron, so these are three perceptron, 3 layers we have. So these are, this is layer 1, this is layer 2, and this is layer 3. Okay, and each of this hidden unit has 2 parts. Can now anyone tell me what are the 2 components of this hidden layer? We have talked so much about it. Can anyone tell me what are the 2 components of this hidden neuron of the hidden layer? What are the 2 components of this neuron in the hidden layer? This one. Anyone wants to answer? So what do we do generally? We take
F and G.
Yes, F and G. And what is F and what is G?
Aggregation and activation function.
Very good, very good. So the first part is aggregation, where we take the weighted sum, and the second part we take any of these activation function to give us the output. Very good. And these output, after applying the activation function, these are called as activations of each node. Okay, so for layer 1, the activation will be a superscript L. Activation for this layer will be a superscript 2 and 3, so on. And when we talk about a superscript 0, so that those are the activations of input layer. And what is the activation of input layer? It is doing nothing. They are just pass-through neurons. So whatever is the X, it will be given as, it will be considered as the activation of layer 0, I can say. Okay. And these are the weight matrices of different layers. So the backpropagation, we can understand it with it consists of two parts. The first one is forward pass and the second one is backward pass. So let's first talk about forward pass. So this is a 3-layer network. This is just an input layer. Otherwise, we have 3 dense layers. Okay. Now, as someone has rightly pointed out, what each neuron is doing, these are biased now. These values are 1. Okay. These are gray ones are biased neurons and its values are 1. So represented by B1 in these equations. Now each neuron is doing 2 things. So this first part, I am representing it with Z. So it is taking the weighted sum and adding the bias. The second part of this neuron, it will apply some activation function on this weighted sum. And the result of this activation function, I am calling these as activations of a layer 1. Okay. So these activations of layer 1 will be considered as as input to layer neurons of layer 2. So this is represented here. Activation of layer 1 will act as input. These are weights and this is bias. So again, we have taken the weighted sum here. Now we will apply some activation function in this particular layer. So it will give us the activations of layer 2. So this will give us the activation of layer 2, output of layer 2, which will act as input to layer 3, which is also our final output layer. So here again, we will do the same thing. We will take the weighted sum and apply activation function on this weighted sum, which gives us activations of the output layer or the final layer. Okay. So this was comparatively easier. Now, once we reach at this point, what we have, this A3s can be considered as output values of each neuron. Now, these output values will be compared with the original labels. Okay, suppose this represents whether there will be diabetes. This represents whether or like what if diabetes had certain parameter. I don't remember right now. Or maybe it's a meteorological department neuron. Maybe they are predicting rainfall, they are predicting humidity, and they are predicting temperature. Okay, so it will give some value. Maybe the rainfall is 130 mm, and original value of rainfall is suppose 165 mm. So it will take the difference. So there will be some cost function. Generally, it is not just the difference. It is, we can have different cost functions by which we can calculate the error our model is making in prediction of some value. How close our model is predicting some value. So initially, in the first forward pass, I can say this model output will maybe far away from your original expected output. Okay, so your error will be large. Now, if your error is large, what we need to do, we need to update these weights. And how to update these weights? That is the main algorithm, which is the means the major step of backpropagation algorithm, which is called as backward pass. So now we have some errors in this. What error this neurons are making using some error function like mean absolute error, mean root mean square error, and there are other error functions as well. Okay. But if we talk about classification, we have binary cross entropy loss. So we have certain loss functions as per our problem. Now, once we have the error, we want to identify what is the percentage of error. Like what is the contribution of error, contribution of each neuron of the previous layer in making that error. What is the contribution of each neuron in making that error? How to do it? There we calculate the gradients. Okay, we calculate the gradients with respect to each and every weight of the previous neurons. And we keep on calculating these gradients till we reach the input layer. And once we have these gradients, we can update the weights using our gradient descent algorithm. Okay. So this is the basics of artificial neural network. Now to do different tasks. So what we have done is, we have done the forward pass and we have done the backward pass and updated the neurons. So this is called as one iteration. People also use terminology epoch, but I won't say that it is technically correct. The more technical terminology for this complete process is called as iteration. And we can have n number of iterations. As we increase the number of iterations, our values will increase. Our accuracy will increase, more updates will be there. And once there are no updates in the weight, then we can say that this is the maximum accuracy which we can obtain from this particular neural network. Now, some design paradigm I want to consider, I want to talk about. It's like I'll go all this with this quickly. So this is input layer, this is output layer, and these are my hidden layers. Now the number of nodes in these hidden layer is again a hyperparameter, or I can say a design decision. So more the number of neurons, generally we say that output is more, because then we are able to identify what is the contribution of each neuron in updating the weights and contributing to a particular task. Okay, as we increase the number of hidden layers, generalization capability of our model increases. Now, what do I mean by generalization capability of the model? The generalization capability of the models is that the initial layers are responsible for these shallow features. That means there is a face, okay, there is some round object. As we go deeper, we get minute details. Minute details means maybe features, the specific features. Okay, if the edges are combining like this. Okay, this particular object is there, it is a face, this is a ball. So more deeper features or more minute details are there in the hidden layers. Okay, so again, if we have very complex problem, we go for large number of hidden layers. But if our problem is not that complex, small number of hidden layers will also work. And that's all I want to share in this introduction to artificial neural network. If you have any questions, you may ask. Then I'll quickly go to this demo part as well. So if there are any questions till now, we can take quickly. So
So are there any questions from the audience in case if they have, so they can ask, ma'am? Seems, ma'am, there are no specific questions as of now.
okay. So let me start. Let me launch the notebook, which help you as well to see how to train whatever discussion we had, like back propagation part, updation of gradients. Let me show you quickly how it can be done using Python. So these days, we generally don't use Python. We have more frameworks available, like we have TensorFlow, Keras, we have Python, PyTorch. So all these calculation of gradients, doing back propagation, all these things are handled by these frameworks. So in that way, it's very nice. But I have also included a portion where you know how to do it on your own. If you want to design neural network without using these frameworks, you should be able to do it. So I hope my screen is visible to everyone.
Yeah, it's now visible, ma'am.
Okay. So this is like the basic, this notebook, I'll share it with you. Now,
Okay.
what we are doing in this particular problem is that we have some number of images. Now, those images are not represented as per proper images. If you know that each image is made up of pixel values, and these pixel values are nothing but the intensity values, or maybe if we talk about, so we have 0 to 255 intensity values, and if we have 250 means 25 cross 25 image, it means that the number of pixels in that image are 625. Okay, so I can represent these images in form of a one-dimensional array. So I'll share this data set, and also I'll share this code with you. You can just run it on your own. So yeah. So these are some of the libraries. If you are not very familiar with it, you can just unmute yourself and you can ask me the doubts anytime you want to. So these are basic libraries in Python, like basic linear algebra libraries. These pandas, if we have some arrays or CSV files, it is very useful library for accessing these CSV files and manipulating the values. So this is the data set we have. Okay. So the data set is like pixel values, and to show it in form of an image, I have just reshaped it in 64 by 64. Okay. So we have like these number of values. So it contains only two type of data. So data is related to sign languages, sign language 0 and sign language 1. Okay. So we have these two binary classes. So this is all about data part. Let me come to the backpropagation. Yeah. So here I have again specified what do we mean by this backpropagation. What do we mean by cost? I'll take the gradient value and go in the negative direction of gradient. So the cost function here, which I have taken, is the binary cross entropy loss. So let me just quickly come to this part. So this is my artificial neural network. Okay. First, I initialize the parameters. So what I am doing is I am randomly initializing these weights. Okay. So I am randomly initializing these weights since there are two input values. Means only two type of values are there, either 0 and 1. So these are weights and I am randomly initializing it, and bias, I am taking the biased value as 1 for all the values. So this is like forward pass. These are my activations. So this is first the Z value which we have taken. It is just taking the sum. It is doing the weighted sum. Okay. And we know that either I can take the weighted sum or I can take the dot product of I can say dot product of two vectors. Okay. So here I have taken this dot product to get the Z value, that is mean the weighted average, weighted sum. And in that weighted sum, I have added the bias value. Okay. After this, what we do, we apply some activation function. So this is my 10H is my activation function. So this gives me the activation for the first layer. Second, I use these activation functions, take the weights of the second layer, apply the bias for the second layer, and do the weighted average. So that is my Z2. Again, using the sigmoid activation function, Ujjwal, we have discussed that there are multiple type of activation function, and what they are providing us is that instead of providing output as 0 and 1, they provide us a real number between a certain range. So when we talk about sigmoid activation function, they provide us a value between 0 and 1. 0 and 1. If we talk about 10H activation function, it provides us an output between -1 to +1. Okay. In the slides, it is given the shape of activation function as well. So 10H is considered as a very good activation function in most of your classification problems. So in the first case, I have taken the 10H as the activation function, and for the calculating the activation of the second layer, I have used sigmoid activation function. And this is the like dictionary which I have created to store the activations, and I call these Z as logics. Okay, so these logics and activations in a dictionary. And this is the cross entropy function because it gives us the value whether the output belongs to class 0 or class 1. So whatever output, so we have two values. If suppose the first two output neurons, the first belongs to class 0 and the second belongs to class 1. Now whichever neuron get some value or more value, that means that this object or the current instance belongs to that particular class. Okay, so this is nothing but the formula for calculating this cross entropy loss. Now the back propagation, this is saying that we are taking the gradients. So this is how we are doing it, okay? And then this is the gradient descent approach. We have some learning rate defined. Right now this learning rate is 0.01, and we calculate the gradients of these weights and biases and update the parameters which are weights and biased accordingly. And once we have this, we can create this model and use it for the prediction. So this is like cost after each iteration. So this cost is decreasing. So I can say that yes, my model is learning. So after each iteration, it is going in the right direction so that its cost is learning. And if I want to do this prediction, we have to reshape it, and then I can predict the output. Now same thing, this was like plain Python code. I would suggest that you go sit and try to understand each and every step. So whatever theory we have discussed, like taking the gradients, calculating, applying the activation functions, calculating the activations, all these things will be clear to you. And once you are able to do it, these days we have many deep learning frameworks available which allow us to doing all these things on the go. We don't have to worry about calculation of gradients. All these things will be done automatically. So this is the implementation with the Keras library. I have included it for your convenience, but I think that part will be covered in the coming sessions. So even if you want to skip this part, you may skip. Okay. And but one thing which you will appreciate here is that these dense layer, we have discussed that dense layer is the one where each neuron is connected to each neuron of the previous layer. So that layer is called as fully connected layer or dense layer. So the Keras use the same terminology if they want to add another layer. So we just have to add that we want to add a dense layer and how many neurons it has, how many units it takes. So there where we can specify it here as well. And previously we have taken 10H activation function. Here we have taken ReLU as the activation function. And in the last final output layer, it is just giving us 1. So it will give us the probability of the image being belonging to 0 or 1 sign language. Okay, so this will give us some value between 0 and 1, so we can decide a threshold value whether we want to go for value greater than 0.5 or whatever. Okay. So this also gave us the output. So we'll share it with you, and if you have any doubt regarding this, you can ask. So I think that there are no questions. Thank you everyone for your time.
There are no questions. Yeah.
So thank you everyone for your time. And even if you face any difficulty, you can send me a mail anytime you want to. So
thank you, ma'am. Thank you. Thanks a lot.
Yeah, most welcome. And I'm really sorry for the technical problems which were there in the beginning of this session, due to which we have extended some we have taken some extra time, but thank you all for your cooperation, and thank you.
Thanks a lot. Thanks for a